We're going to start off with Andy Moore talking to us about the origin of exceptional type 2A and 2B diamonds.
Okay, great. Thanks for the invite to give this talk, which I'm doing on behalf of myself and Herb. It's a project we've been working on for some time. And just to kick off some background, which most of which was covered by Farnes in his talk yesterday, but diamonds, of course, the high pressure form of carbon, and most diamonds have nitrogen as trace impurities, and these nitrogen-bearing diamonds are called type 1 diamonds. There are a variety of different subgroups, but those aren't important to us at the moment. But nitrogen absorbs the blue wavelength, and so these diamonds, nitrogen-bearing diamonds, often have a yellow color. Now, the inclusions in diamonds link them to the two main rock types of the upper mantle, peridotites down here in the bottom right, eclogites in the top right. And so the majority of diamonds seem to have been formed in association with these two rock types. On the left is the carbon isotopic signatures of these two groups, eclogites up here and here peridotites. This just shows the proportion of carbon-12 to carbon-13, with the light isotope carbon-12 increasing to the left. And both eclogitic and peridotic diamonds have a prominent isotopic peak at around -5, which is considered to represent the carbon isotopic signature of the upper mantle. And the eclogitic suite has a tail towards light carbon isotopic signatures. Now, these two graphs show what happens with compositions of, on the left, peridotic, on the right, eclogitic or basaltic composition with increasing depth in the mantle. So, for example, with increasing depth, olivine will revert to wadleyite and then to ringwoodite. And in addition to the dominant eclogitic and peridotic diamonds, there's a small population that have inclusions which indicate derivation from depths up to and possibly exceeding 600 kilometers. And these are termed super deep or sublithospheric diamonds, so third diamond paragenesis. Now, while a majority of diamonds have nitrogen impurities, there's a small population which lacks nitrogen. These are type 2 diamonds, so the name simply means nitrogen below detection limit. And as a result, these diamonds have a beautiful white color, and these are the exceptional type 2 diamonds. Can be very large. These are all from Lesotho. This is the Lesotho Promise, which weighed in at 603 carats. So these are the diamonds we will be talking about today. Then there's a subpopulation of the nitrogen-free suite that has boron as an impurity. And when boron's present, this gives the diamonds a blue color. And these are the type 2B diamonds. Now, the majority of the largest gemstones are all exceptional type 2s, or certainly the majority. These are the three largest. At the top, the famous Cullinan stone, which weighed in at over 3,000 carats or over 600 grams. And something that probably strikes everyone about these stones is that they don't have the nice crystal shapes which Farnes discussed in his talk yesterday. They're all irregular. And this is a characteristic of these stones. One of the other characteristics is that they often have graphite as an inclusion, but other inclusions which might link them to one or other mantle paragenesis are rare. And because of this, the origin of these diamonds has long been enigmatic, and one of the important reasons is that inclusions are very rare in these stones. Now, in a study by Evan Smith and co-workers published in Science in 2016, They coined the acronym CLIPPER for these exceptional type 2 stones, which stands for Cullinan-like, large, inclusion poor, relatively pure, in other words, nitrogen below detection limit, irregularly shaped and resorbed. And I've highlighted it irregularly shaped because you can generally simply recognize one of these clipper diamonds on the basis of its irregular shape with a high degree of confidence. So the irregular shape, one of the very characteristic features of these diamonds. They're highly important economically because they can have a big impact on kimberlite economics. So the presence of these stones in Litseng gives the diamond parcel an average value of when I last heard, $3,000 a carat. And this makes Litseng one of the lowest, in fact, the lowest grade diamond or kimberlite producer in the world. So it's obviously important to find out if these stones are present. And at the moment, the only way of doing this is to get a bulk sample, which is expensive. So it would be ideal to develop some sort of a proxy for predicting whether they are present or absent. And this requires an understanding of their formation. And there are two main models. The first, which is probably the most widely accepted, is that they have a super deep origin. And this is a model developed by Evan Smith and his co-workers. And if this model is correct, then developing a proxy, a predictive proxy, means that we have to understand low mantle processes and mineralogy. The second model, which I've been pushing for several years, is that they're part of the megacrys suite. In other words, have a lithospheric origin. And if this model is appropriate, it means we've got to understand the origin and mineralogy of the megacrysts. So let's kick off by looking at the evidence for a sublithospheric origin. And this was based on screening of diamonds at the Gemological Institute of America by Evan and his co-workers, looking for type 2 stones with inclusions that differed from those in the known lithospheric and sublithospheric parageneses. In other words, different from those of the eclogitic, peridotitic, and known super deep diamonds. And they found diamonds which had sublithospheric, these are all nitrogen free, obviously, and they found nitrogen free stones with inclusions which indicated a sublithospheric provenance. It was a very, very meticulous study. And on the basis of this, they inferred that the Cullinan diamonds were, the clipper diamonds had a sublithospheric provenance. And it should be mentioned that one of the things they picked up was that the graphite inclusions, which are very common in type 2 diamonds, often were masking inclusions which hadn't previously been recognized. So a very careful study. And on the basis of these sublithospheric inclusions in these nitrogen-free diamonds, they inferred a sublithospheric origin for the clippers. A lot of the inclusions were nickeline alloys. But one of our concerns is if you look at these diamonds, a majority of the stones studied are quite inclusion rich. And this conflicts with the definition of clippers, which are inclusion poor. So the abundance of inclusions raises a potential red flag for this model and possibly queries whether these diamonds are in fact linked, that they type 2 stones, certainly, but whether they link to the clipper suite. And this problem is illustrated at Cullinan, where you've sampled sublithospheric, peridotitic, and eclogitic diamonds, so a wide section of the mantle, and these diamonds at the bottom are the clippers from Cullinan. It's an important clipper producer. They have light carbon isotopic signatures biased towards carbon-12. And in these associations that you also find there, each of these associations has the black symbols are nitrogen-free diamonds. So in each of these three associations, they're nitrogen-free and by definition clipper diamonds. So this means that if you take this population, for instance, quite a large number of sublithospheric inclusions, is it related to the clipper population? These three parageneses are all biased towards isotopically heavier signatures, and this suggests that there isn't a link between, for instance, these stones and this population. So if you find a nitrogen-free stone with inclusions, you have to have reason to link it to the clipper population. Simply having a nitrogen-free stone on its own is not necessarily going to be a clipper stone. And this is further underlined at Letseng. These are the clipper stones, another important clipper producer, again biased towards light carbon isotopic signatures. And these are the sublithospheric stones. The black ones are the samples studied by Evan Smith and co-workers. They have heavier isotopic signatures, don't provide strong support for a link to this population. Doesn't rule it out. It's a very small population, but it certainly isn't shouting out that these sublithospheric diamonds are linked to the associated clipper suite. Then on the left-hand column is a list of the phases reported in the study, and a majority of these phases are present in alluvial diamonds at Juina, which contain a high proportion of sublithospheric stones. And the Juina alluvial deposit, this is in Brazil, is notable for having hydrogen as an impurity. This is actually rare in diamonds, and Kaminsky and Wirth said that the presence of hydrogen set the Juina stones, sublithospheric stones, apart from other diamond deposits worldwide, and hydrogen was reported from some of the diamonds in the study. So I believe this raises the query, is this a new paragenesis that differs from the known sublithospheric parageneses? I think this is debatable. Then a further problem with, not simply with their study, but just with inferring a sublithospheric provenance, is that CiSO3 has three polymorphs. The low pressure one is wollastonite. There's a high pressure one with a perovskite structure. This is rare. It's been reported in 1 and possibly 2 diamonds, but there are a number of diamonds that have the intermediate pressure polymorph. The blue area shows the stability field. It's named Brayite in honor of Gerhard Bray, the kimberlite experimental petrologist. And a number of occurrences of Brayite inclusions have been found. And when they've been present, it's been assumed that they have inverted from the high pressure form. But a number of workers have pointed out that this is problematic because Brayite can also crystallize under sublithospheric pressures in the appropriate compositions. So carbonate-rich and calcium-rich composition will crystallize Brayite at lithospheric conditions, in other words, down to about 7 gigapascals. So that raises the question, if you have a Brayite inclusion, what does it mean? And for example, this is a nitrogen-free stone. These are black graphite inclusions, probably. It's from the Williamson mine. The pink color, as Farnes mentioned yesterday, is the result of plastic deformation. And the morphology is shouting out that this is a clipper stone. It's a fairly large stone. So I don't think much debate about that. But what do the Brayout inclusions tell us? It was inferred to be in evidence for a sublithospheric provenance, but I think it's completely compatible with a lithospheric provenance. So in other words, the presence of Brayout inclusions isn't conclusive. So these are some of the concerns that we have about the sublithospheric model. Firstly, many of the samples were inclusion rich. It infers a hitherto unrecognized paragenesis, but most of the phases also occur in the sublithospheric population at Juína in Brazil. There's the problem in interpretation of Brayout. And then at Letseng, although there's only a small number of sublithospheric diamonds, they don't shout out for a link to the associated clippers at this important clipper locality. And we believe that collectively, this evidence argues against a sublithospheric origin for the clipper type 2 diamonds. So let's look at the evidence for clipper megacryst link. This is one of the classic photographs from the Lesotho kimberlite volume of a group of megacrysts. This is a centimeter scale, and the definition of a megacryst by Ben Hart is that they monomineralic nodules greater than 10 millimeters in diameter. The common phases are garnet, illustrated here, olivine, orthopyroxene, clinopyroxene, and ilmenite, and also a number of other rare phases, but including zircons. Now, in addition to these large nodules, you get much rarer inclusions in kimberlite. This is a pyroxene ilmenite intergrowth, and the composition of the phases is very similar to those of the megacryst suite. So this suggests a link to the megacryst suite. That's a large section, and this is a detail of this area in here. And this shows a texture called comb layering, which indicates rapid crystallization or quenching. So the compositions of the minerals link this to the megacryst suite, but the texture indicates that this crystallized rapidly. Then the megacrysts have been divided into two populations, which are often regarded as separate populations. These are the clinopyroxenes, the garnets, and the orthopyroxenes, olivine down here. And the red population is chrome-rich, and the orange population chrome-poor. So the megacrysts are divided into chrome-rich and chrome-poor subpopulations, although these seem to be present in the majority of kimberlites. And very occasionally you seem to see these two associations in the same hand specimen. The gray represents an orthopyroxene megacryst, and this hosts an orange garnet, which matches low chrome megacryst composition, and in turn encloses a garnet with compositions very similar to the chrome-rich suite. So very occasionally you see these two populations in the same hand specimen. So just to summarize some of or emphasize some of the most important characteristics, firstly, large size, a subset with textures indicating rapid crystallization, chrome-rich and chrome-poor subsuites, which very occasionally coexist in the same hand specimen. Zircon is a minor member of the megacryst suites. Where these have been dated, they give ages that are very similar to the host kimberlite. So this indicates crystallization just prior to incorporation. So this suggests that the megacryst suite had a very short mantle residence time. And you sometimes see carbonate inclusions, and this is pointing to a carbonate-rich parental magma. Now, before we talk about the clipper diamonds, the exceptional type 2 diamonds, we're going to have a diversion and just discuss some of the characteristics of an enigmatic group of diamonds called phragmocytes. They're polycrystalline, composed of tiny little crystallites. Their origin is considered highly enigmatic. This is another specimen, and this is a somewhat coarser specimen over here. So polycrystalline diamonds, phragmocytes, and what do they tell us about diamonds in general? Now, these are some of the most important characteristics. They can be quite large. They're polycrystalline, interpreted to reflect rapid crystallization. They have inclusions which have been classified as websteritic, but there's a problem with websteritic compositions because they show a strong overlap with those of the megacryst suite. So it's long been a problematic to distinguish between the websterites and the megacrysts. We'll talk about that shortly. These inclusions have been divided into chrome-rich and chrome-poor subsuites, but occasionally you see them in the same diamond. And occasionally these inclusions are zoned, and this is interpreted to reflect a short mantle residence time. Zoning wouldn't last long under mantle conditions, so crystallization shortly prior to kimberlite eruption. And some of them have carbonate inclusions. Then extremely important is that they have a very unusual and very diagnostic carbon isotopic signature, which is shown here. The bottom 4 panes for individual localities. The top is a composite. The red are phragmocytes with inclusions, and the lighter color inclusion-free phragmocytes. And at each of these localities where you've got a significant sample size, the majority are characterized by light carbon isotopic signatures with a peak somewhere around -18 to 20. But in each of these, there's a subpopulation with heavier isotopic signatures. So this overall signature of a light carbon isotopic rich composition associated with diamonds or phragmocytes with a heavier carbon isotopic signatures is very characteristic, unusual overall characteristic, and very different from that of the eclogitic and the periditic suites. In terms of composition, this blue line shows the range of compositions of garnet inclusions from a group of samples from the Vienna Museum in Austria. The provenance of these phragmocytes isn't certain, but it's believed to be Southern Africa and probably Botswana. And it's characterized by a range in MGFE, but relatively invariant low calcium contents. And this is typical of websterites. So on this basis, these have been classified as websteritic. The crosses are inclusions in Venetia diamonds, very similar low calcium with a range in MGFE. This includes some phragmocytes. So these have also been classified as websteritic. The orange symbols, however, are megacryst compositions, and you can see there's a strong overlap. So this raises the question of whether these are linked to the megacrysts or the websterite suite. So compositions alone are not definitive, so we need to look at some other characteristics. And here I've compared the megacrysts to the phramosite. Both can be large by definition. There's a subgroup of megacrysts showing rapid crystallization textures. Phramosites show rapid crystallization textures. Both are broadly coeval or formed shortly before kimberlite eruption. Both have chrome-rich and chrome-poor subsuites, which may coexist in the same hand specimen or the same diamond. Both have carbonate inclusions and another number of other similarities. And we feel that these parallels are so dramatic, in addition to the compositional similarity of the phramosite inclusions to the megacryst suite, that this links the phramosites to the megacrysts. In other words, this is part of the megacryst suite. And this has a very important corollary, we believe, or we submit, that the megacryst suite must now be acknowledged as a distinct diamond paragenesis. That's in addition to the eclogitic, peridotitic, and sublithospheric, which includes phramosite diamonds, and that these are characterized by a highly distinctive carbon isotopic signature, which is shown again down here, eclogitic and peridotic signature on the right. And if you compare that to the clippers from Cullinan and Letseng, two important clipper producers, they're remarkable parallels. The majority at Letseng and Cullinan have light carbon isotopic signatures, but in both there's a subpopulation with heavier isotopic signatures. And just to compare them, these are the sublithospheric diamonds from Letseng. And we believe that, or we submit that there's such a similarity between the unusual signatures of the phramosites and the clippers at these two important localities, that this is arguing for a link between the clippers and the phramosites, with the implication if the phramosites are megacrysts, so are the clippers. And just to underline this, textural characteristic of the megacrysts is they're large, greater than 10 millimeters. This also applies to the exceptional diamond, type 2 diamonds, the clipper diamonds. And I don't think this is a trivial petrographic observation. I think it's significant. So this raises the question of how the megacrysts form, and this is a further rather controversial signature. It's a controversial issue, but at Monastery, John Gurney and co-workers showed that the megacryst suite formed isobarically, but over a wide temperature range extending towards the diamond stability field. This is the graphite diamond inversion curve. The high temperature megacrysts were olivine, orthopyroxene, clinopyroxene, garnet, and the low temperature ones, ilmenite and zircons. So a range of isobaric crystallization over a range of temperatures. One of John Gurney's students, Jenny Hops, showed at Jwaneng you had a similar characteristic, isobaric crystallization over a range of temperatures extending into the diamond stability field. And Ben Hart and John Gurney proposed a model along these lines to account for this isobaric crystallization over a range of temperatures. And this is my attempt to represent it. So this is my artwork, but I'll try and give an outline of their model. That they envisaged a pooled magma body in the mantle, surrounded by a thermal aureole. They were silent on the nature of the magma, but I believe it's the kimberlite magma, but this isn't critical for the model. And they suggested that small volumes of this magma were injected into fractures in the surrounding thermal aureole, and these crystallized as pegmatitic veins. So the megacrysts are parts of pegmatitic veins crystallizing down this thermal gradient. And we suggest that the megacrysts, the type II diamonds, the clippers, are part of the megacryst suite, and they formed at the low temperature end of this range. So something like this. As you get into low temperatures, you potentially cross into the diamond stability field, and diamond can crystallize. Presumably, the mantle rocks must have buffered these megacryst magmas to low FO2, which is also important for crystallization. So we propose that these exceptional type IIs are low temperature members of the megacryst suite, and at these low temperatures, you'd have had olivine and orthopyroxene and garnet fractionation. So these would probably be carbonate-rich and calcium-rich residual liquids. So these are just the compositions that could potentially crystallize brayeite as a stable phase. And this could account for brayeite in some of the exceptional clippers, as in that pink stone from Williamson. Now, what we further propose is, at the time of crystallization, you'd have probably got to heralding crystallization, fracturing of the mantle surrounding this magma body, and this would result in volatile loss from these residual magmas. Oh, sorry, I didn't point out, Dan Schulze has pointed out that the megacryst suite, the low temperature megacrysts, would be above the solidus, and he's noted that there would have been residual liquids. Sorry, I should have pointed that out. So these residual liquids left following megacryst fractionation. And we suggest that fracturing of the mantle prior to eruption would result in volatile loss. And if a magma loses volatile loss, this can trigger rapid crystallization. So we propose that this explains the formation of these nodules with quenched textures, and also the formation of the phragmocytes. So phragmocytes and the exceptional clippers, part of the megacryst suite. So let's just look at how this potentially tells us something about possible proxies for predicting these clippers. Now, the triangles are group 2 kimberlites, and none of the group 2 kimberlites is an important clipper producer. The clipper producers, or the important ones, are all group 1 kimberlites, Arapa and Jwaneng in Botswana, Jwaneng and Premier in South Africa, Letseng in Lesotho. So all of the important clipper producers are group 1 kimberlites. And so the first question is, why is it that you don't see clippers in the group 2 kimberlites? And this is a model that I suggested some time back. This is looking at the megacrysts in monastery. This is the study of John Gurney and co-workers. And they showed that the olivine megacrysts showed, with increasing iron content, showed progressively increasing titanium. And then these garnets were joined by ilmenite, and these are ilmenite garnet intergrowths often, and this resulted in a decrease in titanium. I don't know if you can see the bottom line, but this would be decreasing magnesium over here, and decreasing magnesium is broadly a proxy for decreasing temperature. So you'd have got crystallization of the monastery, the group 1 garnets over a relatively wide temperature range. These are garnet megacrysts from star, which is a group 2 kimberlite. They show a much more restricted range, which don't get down to the same iron-rich composition. So we suggest this is indicating for some other reason not understood, but crystallization didn't extend over the same temperature range. So we suggest that in the group 2 kimberlites, relatively extensive megacrystallization takes you into the diamond stability field, but in the group 2 kimberlites, much less evolution of the megacryst suite for reasons not understood, but that's what the chemistry is saying, and the crystallization ends up in the graphite stability field, and as a result, the clippers don't form. So potential link between megacryst compositions and the absence of clippers. And this is further illustrated by olivine megacrysts, because not only are clippers rare in the group 2 kimberlites, but rare or absent, but they're very rare in the lac de Gras kimberlites in Canada. Now, if you look, we're now doing a quick diversion into olivines. This shows olivines from the Kimberley pipes, and the important feature are these gray symbols. These are olivine rims, and this would be a composite of all the Kimberley kimberlites. And relative to the composition of the rims, you get a group of iron-rich olivines. This is from a paper by Roger Mitchell and co-workers, and they've suggested that these are megacryst olivines, which is something that I'd suggested previously as well. So these iron-rich olivines relative to the rims are regarded as the chrome-rich megacryst population. This illustrates this for Letseng, an important clipper producer. These are the olivine edges, the crosses, and these are the relatively more iron-rich olivines, and they show reverse zonation. And the cores of these olivines go down to relatively iron-rich compositions, round about magnesium number of 81. Now, if you look at lac de Gras, the crosses again are the olivine margins. These are the relatively iron-rich olivines, and they show a relatively small range in MGFE, as far only as magnesium number of around 90. Finch and Newlands are group 2 kimberlites. Again, these are the edges, the crosses, and the iron-rich olivines again never get down to iron-rich. The iron-rich compositions that we see at Letseng, for example, they only get down to just about FO84, or magnesium number of 84. And so again, we get back to the same diagram. At Letseng, a wide range to iron-rich compositions suggests a wide temperature range of crystallization of the megacryst olivines, potentially going into the diamond stability field. But at places like Leslie was one of the kimberlites of the joining of the lac de Gras field, much less evolution, and you don't get out of the graphite stability field. So this is starting to look as though we might be on our way to getting a proxy to predict the presence or absence of clipper diamonds. But this illustrates one of the problems. The diamonds here are megacrysts these are actual megacrysts from monastery. They go down to very iron-rich compositions. That's great because clippers have been reported from monastery. So in monastery, the association seems to work. The triangles, though, are olivines from the Colossus kimberlite on the Zimbabwe craton. They also go down to fairly iron-rich compositions, but to my knowledge, clippers haven't been produced from Colossus. The diamonds that it's been mined and the diamonds recovered have all been small. So at Colossus, for whatever reason, maybe a different craton, the link between the iron-rich compositions isn't giving us evidence for the presence of clippers. So I think this is where we are at the moment, that megacrysts can help explain the absence of clippers. That's, I suppose it's a bit of a step forward. It's not foolproof in predicting the presence of clipper diamonds. I don't think we've cracked this. It's still work in progress. And I believe that the key is going to be to refine our understanding of the origin of the megacryst suite. But an important corollary is that if there's a link between the range in megacryst compositions and the absence of clippers, I think this is strong additional evidence for a link between the clippers and the megacryst suite. Some intriguing evidence for the possible age of clipper diamonds, going back to this diagram where we pointed out that in each of the three mantle associations at Cullinan, the old formerly known as Premier mine, you get nitrogen-free diamonds, those are the black symbols, and then there's a spectrum of compositions into nitrogen-free diamonds. So in each of these, there's a compositional continuum from the nitrogen-free stones here as well into nitrogen-bearing compositions. So there's not a single box for group 2 kimberlites, type 2 diamonds, but in each association there's this compositional spectrum from nitrogen-free to nitrogen-bearing. And the diamond on the left is a nitrogen-bearing diamond. It's that's obvious from the yellow color, but this intense yellow-orange color is typical of a small subgroup of type 1 diamonds called type 1b diamonds, and these are characterized by the presence of single nitrogen atoms. So the nitrogen impurities are scattered through the carbon lattice. This is a fairly big stone. It would be nearly 14 carats, 14 millimeters across. And these 1B diamonds don't last long in the mantle, because what happens is very rapidly, certainly over less than 1 million years, the diamonds start, the nitrogen starts reorganizing itself into pairs of atoms. So this transition from the 1B to the paired nitrogen atoms takes place in less than 1 million years. So when you find these rare type 1B diamonds, they're young diamonds. They formed shortly before being caught up by the kimberlite. And one of the features that I think should strike you about this is they don't have nice crystal form. They're highly irregular, and in texture they look remarkably similar to the exceptional type 2 suite, the clipper suite. Another one here. This is the Cullinan diamond again, and we pointed out that this irregular morphology is such a characteristic feature of the clipper diamonds. You can actually recognize them on the basis of their morphology. And we suggest that the clippers and these 1B diamonds are part of the same paragenesis, the nitrogen-free extreme and a nitrogen-bearing extreme. So the implication is if these yellow 1B diamonds are young, the clippers are also young, and of course that's perfectly compatible with the megacryst model. And I think you've probably heard enough of my voice, so we'll sign out there. Thanks very much.
Thank you very much, Andy. That was a fascinating look at some really beautiful diamonds. We have plenty of time for questions. So if you'd just like to raise your hand, put a question in the chat, or even just ask your question.
Andy, just a question from me on whether or not you believe the diamonds, the type 2 diamonds with inclusions, you're saying they're not part of the Clipper suite, but do you think they still come from super deep regions of the mantle?
Yeah, sure, Craig. I'm not. I don't think there's any doubt that some of the stones that Evan and co looked at were sublithospheric. There's no question about that. I mean, that was an important study, and you know, some of their stones were 10 carats, and it raises very, very important questions. I mean, how do you get a 10-carat stone to the surface? And of course, it was telling us a lot about the deep mantle. So you know, very important study. But we would argue simply that the stones that they studied, the majority of them were sublithospheric indeed, but not clippers.
Andy, and what age data do we actually have, so to speak, for these big stones, if any, or reliable data?
Well, the only I don't think we have any data, John, and the only evidence that I know is this evidence that I've discussed, that the morphology just is so striking. I've seen not a big cross section, but other type 1b stones that they produced quite a few of them in that Nauja pipe in, I think that's how you pronounce it, in Canada. And all of those were irregular stones, highly unusual morphology. And if that was white, you'd have said it without any hesitation, it's a clipper. So that's the only evidence I can give, is the morphology links this to the clippers. These are young, there's no question about that. I don't think that's debated. And so I think, if, you know, the fact that every one of the parageneses shows a range from nitrogen-free to nitrogen-bearing, I don't think the clippers need to be different from that. And they've actually shown that there is a range, you know, there's some debate as to what you should call a clipper diamond. Should it be the detection limit, which used to be 20 ppm? Should it be 5 ppm? So we know that there's a range from at least 5 to 20 ppm, and probably more than that if you analyzed enough stones. But Farnes pointed out that the producers are very stingy about giving us stones to analyze.
Andy, there's a question from Mike Lynn on the chat. You just repeat the characteristics of the diamonds categorized as definitely sublithospheric?
That was based on the inclusions. For instance, there's majorite garnet, and that certainly is indicating a deep origin. And then there was some brayite. Now brayite, some of it may be inverted, the inverted perovskite structured form, the high pressure form. So we're not disputing that some of them might be inverted perovskite structured CaSO3, but the problem is that CaSO3 can also crystallize in the lithosphere. So basically, some of the inclusions are certainly sublithospheric.
I mean, the other thing that works quite well, obviously, Andy, is the light carbon isotopes. I mean, that feature also seems quite consistent.
These are the signatures, isotopic signatures of sublithospheric suites. And you can see that, I mean, some of them go down to light isotopic signatures. A lot of them have, at individual localities, are heavier. But none of them, for instance, the Jarvis-Fontaine suite overlaps the light part of the population at Letseng and Cullinan, but it lacks the heavier population. So you know, you don't get the striking. These ones are perhaps more similar, but the peaks up at what's this, -24. So collectively, the sublithospheric population does cover a wide range, but at individual localities, these look very different. Whereas with the Framersites, you know, there's such a parallel between the Framersite diamonds and the Clippers. And then, of course, there's the, you know, one of the reasons for light isotopes is that you've got subducted material. But Cartinier has for a long time argued that, and I don't think the two models are exclusive, that if you have fractionation of a magma in the mantle, you'll lose CO2, which will take off the heavier isotope, and that the diamonds will progressively become lighter. So not many people seem to like this model, but you know, what you're saying is that the light isotopic signature is compatible with subduction, but there are other potential models that can also give you light isotopic signatures. And the megacrysts, of course, are lithospheric. They're not deep.
We've got another question in the chat box from Sean Johnson. What are your thoughts on the newly discovered Davamayoite mineral? If I pronounced that one too badly, for classification of clippers. Why don't we see more of this mantle mineral in deep mantle derived diamonds?
Yeah, that is the only verified example of the uninverted form of CAPV. So it doesn't seem to, the argument is it doesn't seem to survive, it inverts. And so some of the Brayite inclusions may be the inverted form of CaSiO3 and are generally assumed to represent inverted Dave Mayoite. But the problem is, are all Brayite inclusions inverted from the perovskite structured form? We argue that they can actually, not only we, a number of others have pointed out that the Brayite can crystallize under lithospheric conditions.
Yeah, I think it does, Andy. I mean, I think one of the things, and Farnes alluded to that, and we've talked about it, you know, you need more information, research on big diamonds or inclusions if they exist from big diamonds. I guess, unfortunately, for understandable reasons, you know, so much work has been done on, you know, generally small diamonds, and mostly it was done before we really appreciated the importance of the big clippers.
But just getting back to Brayite, you know, if you have a kimberlitic magma or any magma and you take out olivine, orthopyroxene, and clinopyroxene, you're going to end up with, and the evidence is quite clear that the megacrysts were formed, they have carbonate inclusion, so indicates a carbonate-rich parental magma. And So you crystallize these magnesium-rich phases, and the end magma is going to be calcium and carbonate rich. And, you know, the experimental evidence says this can crystallize brayite as a primary phase. And I suspect, I don't know what brayite looks like, but it may be, you know, simply you're looking at large diamonds. We may just not be seeing them that often. I presume brayite is transparent. So we might find that, you know, with more samples, that brayite is not as unusual as it, or as rare as we thought.